All right, guys, we are going to do some application problems today, including Newton's law of cooling. I have just a couple quick questions, and we may not even solve these all the way through, but could we just real quick review some of the concepts that we did last week? What would be a good idea for the first one? In theory, we could take the log of both sides, but it's going to get real messy. Can we make these both powers of what? 2, yes. This is not 4 to the third or anything, right? So we got to make them powers of 2. 2, 4, 8, 16, 32. So this is 2 to the 5th. And this one is 2 second or squared. So what are we doing with those exponents? Yeah, we can get rid of the base, but it's 5 times the quantity x minus 1 equals 2 times the quantity x plus 5. Everybody okay? We don't need to actually solve that, right? But you wouldn't forget to distribute. Okay, this one I'm anxious about. We may need to do this one all the way through because if you remember anything about these, they get a little messy at the end. If I add the 2, add the 2 over so that it's equal to 0. Okay, yep, no idea where I'm writing. Then we did a little u substitution thing. We said e to the x squared is what this is, and we let u equal e to the x. So we called this u squared plus 3u plus 2 equals 0. So how would that factor? This is an interesting question, I think, because we get u could be -2 or -1, right? What is u? E to the x equals -2, or e to the x equals -1. And what is the last step then? Yeah, we have to do ln of both sides. So we'd have x ln of e equals ln of -2. Or x ln of e equals natural log of -1. And both of those are not possible, right? Can't take the log of a negative number. So that one has no solution. But I just wanted to follow through because you have to do that last step in order to get x by itself. All right, that was a mess. What do we do on this one? Can we cross out all the logs? No. What would we have to do? Combine these into x times the quantity x plus 7. Then we have a single log equal to a single log. So then we can get rid of it. And we'd have x squared plus 7x equals 18. What's the next step? Yes. I get some goofy stuff after that for some of you. All right. And remember, we can't have a negative at the end on that one either. This is a really good question if I could see it, I think. Or maybe that is the whole question. Okay, let's just move it down here. Can I get rid of the logs on this one? No. Does anybody remember what we did? Anybody? Strategy, look at 9A. Log base 9 of 9x I'm going to add this one over to this side, plus log base 9 of x. I'm actually going to add the 2 back over to the other side. Now what? Does that help anybody see it a little more clearly? We can combine these two. Log base 9 of 9x times x equals 2. And then what do we have to do? Ooh, this is not going well today, guys. What do you do when there's a single log expression? You can exponentiate or rewrite. It's the same thing. So we have 9x squared equals 9 to the second, or 81. We divide and get 9, and then x equals plus or minus 3. Can we have a negative? No. Okay. All right. That was a lot of review. All right. Newton's law of cooling is a great application of where you need logs. It says an object that has been heated will cool to the temperature of the medium in which it is placed. For example, the surrounding air or water. The temperature T of the object at time t can be modeled by this equation for an appropriate value of K, but every object has a different K value. So, where T sub T of T is the temperature of the object at time little t. So, right here it's telling you that little t is time. Okay. T sub m is the temperature of the surrounding medium, or sometimes they use T sub s. This is actually the one that we're going to use right here. So this is the final temperature, surrounding temperature, original temperature, surrounding temperature. And T sub m or T sub s are the same thing, okay? I don't know which way it is on the temperature is right next, the formula is right next to the question on the quiz, okay? And then it's e to the negative kt. Now, the little t up there is time. What they're going to do is they're going to give you an initial set of information to help you find k, and then you're going to use k to plug it back in and make a prediction. Okay? Now, it says both of these formulas assume that the surrounding medium temperature essentially remains constant. An example of a Newton's cooling curve is shown at the right. So, I mean, think about this. If you take, for example, a hard-boiled egg out of boiling water and you set it on the counter, it cools fairly quickly, but then it eventually would hit room temperature and stay the same. Everybody good? If, on the other hand, you took that same egg and you put it in a glass of cold water, it would cool faster, okay? But it would still eventually reach a certain temperature and stay. This business about assumes that the temperature of the surroundings remains constant. Guys, if I take a cake out of the oven or a pizza out of the oven and I set it on top of the stove, it doesn't really change the temperature of the surrounding room much, right? Okay. On the other hand, if I took that egg and I put it in a little coffee cup full of cold water, like I took it out of boiling water and put it in a coffee cup of cold water, it really does have an effect on the temperature of the water, right? Because it's such a small surrounding space. This formula ignores that, okay? It assumes the temperature of the surroundings stays the same. All right, moving on. So this is what we're going to use. It says Newton's law of cooling, a cup of coffee has cooled from 92 to 50 degrees after 12 minutes in a room at 22. All of that information is going to help us find K. So it cooled from this, which is its original temperature, to this, which is its final temperature. after 12 minutes, which is T, in a room that's 22 Celsius, which is the temperature of the surroundings. Okay, all those in the first sentence are only helping us find K. Then we're going to go back and use that K value to figure out the second part here. How long will it take the cup to cool to 30 degrees? We're going to redo it where this is our intended final temperature. But we can't have two final temperatures in the first time around. So students get a little confused sometimes if they don't practice this to realize that there's two separate calculations going on here. All right, so the first time it says the final temperature minus the surrounding temperatures. So we had 50 as our final temperature. The room was 22. Everybody good? Equals original minus surroundings, which was 92 minus 22, right? Surroundings. E to the opposite of K, which we don't know yet, but our time is 12. All right. So 50 minus 22 is 28. How did I do, guys? 92 minus 22 is 70. E to the, is it okay if I write that as negative 12K? All right, first step. Yes, divide by 70. And I'm going to leave that as just 28 over 70. This one happens to come out nice, but a lot of times that's a really ugly number. So it's better to just leave it until later. So now I have 28 over 70 equals e to the negative 12k. What's the next step? When k is my variable's in the exponent, I have to take the log of both sides. And for this question, that would be ln would be much easier. So on the right-hand side, I have the natural log of whatever 28 over 70 is, equals, and this guy comes out front, negative 12k ln of e, which is just 1. So the last step is going to be to do what? Divide by negative 12. All right, so I just didn't want to pick up my calculator till I had to. Natural log of, was it 28 over 70, guys? Close parenthesis and divided by negative 12. Did I remember right? Yeah. Okay, 0.0764. I think on the quiz it says to go out 4 places, which would be tenths, hundredths, thousandths, 10,000ths. This just makes kind of a big difference if you round it later. 0.0764, we decided. All right, so then we go way back up here and put that in this blank. Now it says, how long will it take the cup of coffee to cool to 30 degrees? Okay. So we're going to assume that our initial temperature is still is still 92. Okay, the original temperature is still 92, so we're going to use this. But the surroundings are still 22. What are we trying to find this time? Now we're finding little t, right? Using k equals here. And our new final temperature is going to be this one. So we're not using this time anymore, and we're not using this final temperature. All right, so the formula, anybody tell me what's going to plug in here? T sub f is now what? Final temperature is 30. Our surroundings are still 22. The original temperature was still 92. Our surroundings are still 22. E to the negative K, which is opposite of K, point, so it's going to be negative 0.0764 T. Okay, what are the steps? Do these subtractions, then what? Divide by the 70, so we have 8 over 70, and I'm just going to leave that. Then take the natural log of both sides. This guy is going to move out front. So I have the natural log of 8 over 70 equals negative 0.0764 T ln of E, which is just 1. So my final step is to divide by this, and I will have the time. So the process of solving is very similar for all of them. Was it 8 over 70? And then divided by negative 0.0764, right? So we get about 28 minutes, 28.4 minutes. So maybe that's the coldest you like to drink your coffee, or maybe it's the temperature you like to drink it at. You know, you can have 28 minutes till it cools down to drinkable, or more likely it's 28 minutes till it's too cool for you to like to drink it, right? Something like that. So the time takes is 28.4 minutes. Let me go back and fill that in. All right, so that's Newton's law of cooling. We'll practice it one more time, maybe. Do we get to talk about cake? Oh, I love cake. Okay. Example 2, a cake is removed from an oven at 350 degrees. So its original temperature, you guys know this about stuff, right? If the oven's at 350, then basically whatever you took out of it is at 350. Okay, and it cools to 120 degrees after 20 minutes in a room that was 65. How long will it take for the cake to cool down to 90? Okay, maybe we can't frost it till it's down to 90. So, what are we starting with? Can you label some stuff for me here? 350 is what? What is 350, guys? It's the original temperature. Thank you. Okay, it cools to this. So originally this is our final temp, right? That's going to help us calculate the K first. 20 minutes is our temperature. And the room is this, which is T sub S or T sub M, depending what it says on your paper. All right. We don't use this number yet. Okay. So final temperature minus surroundings equals original temperature minus surroundings times E to the opposite of K times T, which is 20. Okay, that's a mess. Can you still read it? Okay. So 120 minus 65. Anybody is at 55? Did I do that right? And 350 minus 65 is 285. Somebody check me. E to the opposite of k times 20, or negative 20k. So tell me what to do. Okay, then what? Yes. Make sure you're showing work on the quiz so that I can tell where you went wrong if you go wrong. So over here, ln of e is 1, we're left with k. Was it 20 the time? 0.0823, anybody? Destiny says yes. Okay. The little negative is what gets students sometimes. Your k value should not be negative. The negative is part of the formula because it is a cooling formula. All right, so when I go to plug this back in now, I want my final temperature to be 90 degrees. Everything else is the same except for what? What am I looking for this time? The little t, right? For time it takes to get there. So somebody start me out. My formula is way up here. T sub f, which would be what now? $90 minus the room is still 65. The original temperature was 350 minus 65. E to the opposite of k, which will be negative 0.0823 T. 90 minus 65 is 25, anybody? And this is still 285. What do I do first? And this guy goes out front. So I have and then I just need to divide that over here. All right, was it 25 divided by 285? I already forgot. Okay, and then divided by negative 0.0823, right? So we get 29.6. So 29.6 minutes until we can frost it or whatever. Okay? We good? If I give you the formula right next to those, you can find K and then plug it back in and find the other one. They're just a little time consuming because you have 2 steps. But it's very, very similar. Okay. There is one more example on 9. It says there is a half-life formula. Now, it's Not written exactly like this on your reference sheet. I think it looks like this. New, it's R to the T over H. Is that what it looks like on the reference sheet? Anybody have it out? Isabella, is that Seaman? Is that right? Okay. This is what it looks like on the sheet. But it says this is a half-life question, so that immediately makes R 1/2. Okay. All right. This one says P is the initial amount. Well, we have N sub 0. And H is the length of the half-life. Okay. So we still have this value down here of H. Now, what is the number you don't need in this question? Does anybody know? Because it messes people up all the time. Yes, this is the name of the element, okay? That 226 is not a number we're plugging in anywhere. Everybody good? Haley, you with me? Radium 226 is the name of it here, so we don't need that number. Okay. The half-life is, so where does that number go? That's H. Suppose we have a 120 milligram sample. That's our initial amount. How much will remain after, and that's how much time has passed. So for the first part of the question, we have 120. It is being halved, but it's only being halved every time we hit 4,000 years. No, just kidding. That's wrong. It's only being halved every time we hit 1,600 is its half-life. But 4,000 years have passed, so it has been halved like a little over 2 times. Is that right, guys? 1,600, then 3,200, and now it's partway to another half. All right, so type that in very carefully. 120 times 1/2, you could just do 0.5 to the power of, and I'm going to put parentheses, you really don't need them as long as you got the little box. And then it's 4,000 divided by, was it 1,200? 1,600? Thank you. I know I wasn't remembering it right. 21.21, anybody? Okay, that's the first answer here. How long until there will be only 10 milligrams? So what's changing? How long until there will be only? So we want to put the 10 where? We want there to be 10 left at the end. How long means we're looking for what? The time. So starting with 120, it is being halved, and we don't know how long, but it's being halved every 1,600, and we want it to be down to 10. What do we do first, guys? And this is where students somehow decide it's okay to do 120 times 1/2. Is that what we do here? No. When it's an E, nobody does that. But when it's a number, somehow people start doing that. We need to divide by the 120. So then we have 1/2 T over 1,600 equals 10 over 120, and I'm just going to leave that. What are we going to do to both sides? Some kind of log, whatever kind you want. Move that out front. T over 1,600 times the log of 1/2 equals the log of that. Then what? A lot of steps here. Yeah, I would divide by the log of 1/2 next, yep. Okay, my page is getting really, really long here. So I have left t over 1600 equals whatever this lovely decimal is. So then in the end, I finally need to multiply this by 1600. All right. Log of 10 over, I already forgot, 120. Divided by the log of 1/2. I'm just going to put 0.5 because and then after we did that, it said we needed to multiply by 1600. 5736 roughly. There is a question on the final exam and the quiz and the post-test, which is the final exam, I guess, that asks this question in a way that you have to be very careful with your rounding at the end. If this had said how long until there will be less than 10 milligrams, you have to make sure enough time has passed for that to fall below 10, not just to hit 10. Now, did we round up anyway on this question? So we're okay. But if this had been 5735.1 and we cut off that 0.1, would it have gone below 10 milligrams? No, we would have had to round up, okay? So you have to be careful on rounding, but we haven't really hit one exactly like that yet. We rounded this to, what was it, guys? 57? 36 years. Okay. Yes, a very long time. All right, so that's that worksheet. The homework on this is to go is worksheet 10 and 11. There's three more Newton law of cooling questions. There's one about a body. This is actually an easier question because what did they give us, guys? They give us the K. So that one's a pretty easy one. There's another one with a pizza coming out of the oven. I would kind of like us to do number 4 together, and then maybe I can be done unless, well, maybe we'll do there's a couple more I might do with you. Okay, this is off worksheet 10A, I think at the bottom of 10A, is that right? Worksheet 10A, okay. It says logistic growth, and we're going to spend a lot more time on this tomorrow. The growth of most populations in our environment are most correctly modeled by this, where T is time, A, B, and R are positive constants. It says the population of bears in a wildlife area is modeled by this, where T is time in years. If you have a contained area and you have a population of something, does everyone understand that there's probably a limit to what that area can sustain or provide enough food? Yeah. Okay, there's a limit. So we're going to try to put this in, but what do we need when we go to type this in to graph it, guys? I want to put this, we need parentheses around the entire denominator. And if you had an older calculator, you would need another set of parentheses around this exponent. But we got to be careful because I don't want to wipe out that negative there, yeah. So I need everybody typing this in, please, because you're going to have to do this and know how to get it in correctly and find an appropriate window. All right. This question is on the quiz as well, something like this. What was the top 300? Okay, divided by the quantity 1 plus E, am I remembering this right? Which is, 19 and then E. I don't know what just happened. And then there's an E. And we're going to need an exponent, so I'm going to do second ln so that it puts me up in this little box. You don't need a second parenthesis here as long as you have that little box, but I'll go ahead and put one. It's negative. Don't use the minus. It's negative. And then what was it? 0.3. Make sure you put the, it's 0.3, but it's not 0.03, okay? And I can put the 0 in front of it. And then X. Close that one and the whole thing. All right, now, what is X standing for again? Does anybody? Time. Okay, can we have negative time? No. Now, making the Y window can be tricky for students. I'm going to give you a little hint. The top number up here is usually the maximum. It's not always the case, but it's usually the maximum population, so you want to go up that high. Now, can we have negative bears? No. So let's go with 0 to, how many years do you want to look out? Does it give us a clue down in the question? 30 years, right? Or beyond? Doesn't it ask us eventually to go out 30 years? Okay, so I'm going to go 0 to 35 just to be careful. And I think the top maxes out at 300 bears, but I'm going to put in 400 just to be sure. All right, so I have 0 to 35, which I could count by something other than ones if I wanted. And 0 to 400, and I could count by something other than ones. It doesn't matter what the scale is. All right. This is the shape you should always get. If you don't, something's wrong. Now, I say that, but that's not actually true. If you started with too many bears in the area, it would go down before it did this. Does that make sense, guys? Yeah. So if we had a pond and we threw 1,000 fish in the little pond, they'd have to die off until there was a sufficient number that could survive in that. Most of the time, it's growing. We introduce, in this case, a couple bears, and then it grows until it hits a maximum. But it's possible that it could go down. Okay. What does the question ask? After 0 years. So how are we going to do that? Yeah, I'm just going to do trace 0. If you would prefer to go to the table, you could. Initially, there was how many bears introduced here? 15 bears. Okay. And after 3 years, it asks about. So I'm just going to trace 3. There's about 34 bears. After 10 years, starting to multiply a little more quickly, it's up to 154 bears. And then 30 years, it's almost hitting 300, right? 299. And if we kept going, it would just keep getting closer and closer to 300 bears. It would round to 300. When will the bear population be 50? How are we going to figure out when there's 50 bears, guys? Do you want to try to solve this mess backwards? We could go through it, but since we have it graphed, what's the easier way? We could look at the table. Do you remember what we've done to be a little more exact than the table? If we put in y sub 2, a line at 50, and then find the intersection point, that is more exact. We just are estimating with the table, because I got about 4.45 years. The table, you're going to have to say after 5 years or something, because it's going to go by whole numbers. Okay. All right, so someone read me those answers real quick. We did trace for all of these first ones, and we had 15 and then 30 or 40 something, 34, and this was 154. Did I remember that right? And 30 years was basically 299. When will there, in this we put in y sub 2 equals 50, and we did the intersect, and it was 4.45 years. And the max number of bears, what did we say it should be? Should be 300. Okay. There is a question like that on the quiz and on the final, I believe. Okay? We're going to do some of those tomorrow, but actually tomorrow we get to start with a list of numbers. All right. So you need to work on these. There is a formula here you will need to use for these pH questions. And there's half-life questions back here. I'm going to super fast set up number 10 right here. It says if you have an artifact that contains 65% of what was present when it started, so it's down to 0.65 starting from 100%. And it wants to know if the half-life is 5730, how much time has passed. Can you write that down for number 10, just so you remember? That's how you're going to set up and solve that one. We can do one of those tomorrow if we need to. Questions? All right, work on finishing up homework. Tomorrow I'm basically just doing questions, okay? And I will pass out the review for the quiz. Oh, no. Just kidding. Tomorrow is modeling. Wednesday is questions. Then Thursday's review, Friday's quiz. I forgot we have one more section to do. Yes, ma'am.